Now that we established how can we actually assess the whole periodic properties and all the variabilities that might come with them through a different approach that also includes a D block and F block, and what type of variability do we expect from the bonding, it's time to assess what are the basic models of bonding and expand towards a more advanced model that will encompass everything. So when we say bonding, we are fundamentally saying that we want to bring two atoms together and we want them to interact. This is the only way we can actually get into the molecule. And in the approach of organic chemistry, this is done usually with bonding through hybridization, right? So whereas ionic bonds is treated as you're going to have hard spheres, put them together, figure it out, a bonding that is more towards the covalent side can be treated with the approach of hybridization. So you consider that you're not going to have just the p orbitals doing something, but you will have hybrids of s and p orbitals of the final valence shell that the atom is using to interact. These atomic orbitals will hybridize, so you can either do one s and one p, get two hybrid orbitals at 180 degrees from each other, so they will give you a flat molecule. This will be an sp hybridization of the central atom. You can put two of the p orbitals. This will give an sp2, three hybrid orbitals at 120 degrees from each other. Then you can put everything you have. So one s orbital, three p orbital, get an sp3 hybrid in a tetrahedral arrangement of the four hybrids that you get out of that. So 180 degree 0.5 of angle. And this will be an sp3 hybridization of the central atom. This is what is used in organic chemistry to account for the different features of bonding. So an sp3 to sp3 will give you a single bond. sp2 is the thing that gives you the double bond. So then you have a different character of interaction if you have a double bond in between. The sp3 is the one that can give you the triple bond. So this is always related to the hybridization of the central atom. You consider that, well, I'm going to have hydrogen on the other side and only S, I can bond it confidently, right? Then another thing that we do when we want to figure out where are our atoms placed in the moment we assume they bond, because they're not going to be in a random arrangement in space, we want to know where are they located in space, is the use of the VSEPR theory. So the VSEPR theory, which is the acronym of valence shell electron pair repulsion, assumes that the electron pairs that you end up having, either because you have a bond or because you have a lone pair, will be arranged around the central atom in a way that minimizes the repulsion between high electron density area. So bonds and lone pair will want to be far away from each other. You don't want them on top of each other because they will interact. This brings out the VSEPR geometries of possible arrangement, depending on how many bonds you want to put around your atom. And you will always use the lone pair as the thing that must be further away from everything else. Right? So the VSEPR is done by counting amount of bond, counting the valences, and going accordingly. Now, why do we want to move away even from this one as a comfort zone? Because the hybridization is used heavily in organic chemistry. It's a good approximation in organic chemistry, but anything that doesn't have an sp valence shell, so doesn't have those type of orbitals as the threshold orbitals interacting with everything else, will not be accurate. So, and hybridization does not work if you don't have that type of valence. And the core assumption is that to hybridize orbitals, they must be close in energy. But all that discussion of what is the energy of the orbital, depending on how localized close to the nucleus it is that in the breakdown, hybridization is in the moment you actually want to involve orbitals of another character, because between the energy difference and the geometrical difference of the complexity of the electron density volumes for d orbitals and f orbitals, you cannot put them in such a straightforward type of model as the hybridization. The VSEPR will not assume that you can have something that has different degrees of repulsion. The lone pair is a lone pair and the bond is a bond. So this is how you arrange things around the central point in the VSEPR theory. So the lone pair will always be placed to reduce repulsion. All the other bonds will be considered equal. There are moments in which the VSEPR will fail to accurately predict the structure. So it's not that the approximation is not correct. More or less you have that, but species that have the same number of electrons and the different character of what is going on in the molecule will be not predictable through the VSEPR. A very good example is this type of hexaphosphates with the iodine. These are very complex molecules. They do not go nicely with VSEPR. So you might have seen things from more basic approaches to chemistry that use sp3d, sp3d2 hybrids. But we know this thing cannot happen because the d orbital cannot hybridize. They're not close enough in energy to do this type of trick. So you could force it and force the model to work, but it's not going to be accurate, so we're not going to do it. In the VSEPR, the proof of the vague failure will come when you actually look at the experimentally arranged structure of exactly the same molecules that I flagged you before were going to be a failure. The approximation of the arrangement in space is more or less correct, but the real arrangement of the molecule, in this case, for instance, has difference in angles and different in bond lengths that you would not expect from the fact that it's just the same bond. It's iodine, fluorine. Why would you have different lengths? Why would you have different angles? This comes from the feature of the molecule, and this is unpredictable from the basic theory of VSEPR. Same business is with this hexafluoride telluride. So this is where we fail to use basic model to predict more complex arrangements in the moment you actually want to account for the whole periodic table, not just organic molecule, not just something that will fit in a lone pair repulsion with no different interaction present. This is the reason we need to move to something else. It's not that we cannot use this guide as an approximation, but we must be aware that it is the approximation of something else. So the main failure in every time we consider hybridization and VSEPR as theories is that all of those approximations are based on I have atomic orbitals and I do this. I have the valence electrons and the lone pairs related to an atom, and I do this. Everything is related to an atom, but you just brought the whole molecule in interaction. So the pitfall of both of these theories that give a good approximation, but not good enough approximation to actually treat chemistry, is your something belongs to the atom. Your atom is now in a molecule, it does not belong to it anymore. How do we account for something that does not belong to the atom anymore, and we actually treat the thing more holistically? This is something that you've already seen in more intro chemistry courses, so this can use some revision, but we are going to go through how to do molecular orbitals. So why is the molecular orbital theory the one that fits all? Because the fundamental assumption is if you are close enough to bond, your electron clouds are interacting, which is intuitive. You just brought the two of them together. You say that they will bond, so they will share electrons in some way. The electron clouds must be interacting. This means that there is a direct interaction of the orbitals, so of these volumes with a probability to find an electrons inside them. So the wave function that describes the atomic orbital is interacting with the one that is coming from the other orbital. The resulting interaction will be something that creates a new volume because there is two things interacting. Then you will create another thing, something that wasn't there before, but it is the effect of the interaction. So the result of this interaction is a new wave function, a new orbital, a new volume of probability of finding the electrons that will now encompass the whole volume of your two atoms interacting, more atoms interacting, everything. This is the reason why it's called a molecular orbital. It does not belong to the atom anymore. It belongs to the molecule. So you will find with a new shape, a new volume where you could place electrons. Within this volume, there will be a certain probability to find the electron. This is the real nature of the chemical bond and comes from this idea of you put the two things in interactions, then you will create new regions of electron density. One of them will be lower in energy, so it will be the one with the most likely probability of bonding. The other one will be higher in energy, so there is still a potential distribution, but is higher in energy, so the electrons are not going to go there immediately. When we say it's a molecular orbital, this is the example for an easy molecule like H2. You can see the area of bonding that now is not 1s, but is a whole molecule, and the area of anti-bonding in which clearly this thing must be higher energy and it is not occupied in this case. So how do we do the combinations? This is really linear combination. So you take all the atomic orbitals, you combine them together according to a sequence of rules. Note that unlike hybridization, this thing will work for any type of atomic orbital because every orbital can be treated as a wave function and every wave function can interact. So S, P, D, F at any level of n will work. And it will work for molecules of any level of complexity. So the main rule is that for any atomic orbital that you combine, you will find yourself with an equivalent number of molecular orbitals. You cannot just cut out some molecular orbitals because you don't want them. You combine 1 and 1, you will find yourself with 1 and 1. You combine 4 atomic orbitals, you will find yourself with 4 molecular orbitals. Can this be done in full disregard of the energies? Absolutely not, because things needs to be interacting. So only orbitals that are roughly at the same energy can actually interact with each other. Otherwise, it's like things going on a highway at a completely different speed on a different lane. They will not see each other. It's not that they are not there, but they will not see and they will not interact. You will still have the application of the Pauli's exclusion principle and the hand rule. So for anything that is at the same energy, you must first fill, then pair the spins. And you cannot put more than 2 electrons in any molecular orbital. In the same way that you cannot put more than 2 electrons in an atomic orbital, regardless of the character of the orbital. Bonding orbitals are called bonding orbitals because the wave function drops in energy. So this will become the energetic advantage. And the molecule will only form if you actually have the energetic advantage. The anti-bonding orbital is not that is against really the bonding. It's just that can only be approached when you can go higher in energy. Bonding orbitals are filled first, only afterwards you can go to anti-bonding orbitals. The stability of a molecule depends on, is there a natural energetic advantage to do this, or are we going to find ourselves unstable? So the instability can be addressed with the bond order. So the bond order will also tell you something about the character of this bond. So in the bond order, you count the amount of antibonding orbitals and the amount of bonding orbitals. You subtract the antibonding, the bonding, and you divide by 2. Now, this we are going to use in some examples of molecular orbital theory so that we could run through the whole business. We will go from homonuclear to heteronuclear and then give a bit of a prospect of what happens when you actually try to bond a whole molecule with multiple atoms. So if we start nice and easy from the very corner of our periodic table, we find ourselves with fluorine. So 7 electrons in the valence shell. You can see from the electron configuration. Helium will bring 2, so there are 2 in the inner shell, then 2s2, 2p5. So this means that will be 14 plus 4 electrons in 9 molecular orbitals if you bond 2 fluorines together. So if we bring 2 fluorines close to each other, then you have first interaction of the 1s that is not shown in this diagram because it's too inner. If you only use the valence, then you start to interact with the 2s. So the 2s come together. They are exactly the same energy because you have exactly the same molecule. You will have a bonding and anti-bonding symmetrically arranged around the energy of the starting ones. Each of these has 2 electrons according to electron configuration. For every atomic orbital you brought in, you get yourself a sigma and a sigma star, that is the anti-bonding. You place the electrons, so you have 2 molecular orbitals from 2 atomic orbitals, 2 electrons per atomic orbital. So you need to arrange 4 electrons in 4 molecular orbitals. First you fill this, then you fill this. This shell is now full, so it could in theory be disregarded because it's completely built up. You move to the p orbitals. So now you have 2p5, so you have 3 p orbitals with 5 electrons in them, and they are interacting with the one of the other fluorine. This will mean you can have 1 sigma interaction that is straight on. So if you take, for instance, X and X, they will interact with each other. Then you get a sigma and a sigma star, once again, symmetric. This is the most of the gain, the most of the loss. And then you have another 2 on this side and 2 on this side that still need to interact. This will make pi type of molecular orbitals because the interaction is not direct. It's impossible, geometrically speaking. These things are on a Cartesian axis. They cannot make another sigma interaction. So now you find yourself, we started with 3 and 3. So you're supposed to find 6 molecular orbital. If you count, these are 6 molecular orbital. With 10 valence electron to fill, you fill them up from the bottom to the top. It doesn't matter that you need to pass through the pi. It's perfectly fine. The pi is lower in energy than the pi star and of the sigma star. So first you fill, then you pair, then you fill, pair, pair, then you go up. Is this molecule stable? Well, you're going to have how many? You could disregard this one just because this one will get out of the count by itself because you will do 2 minus 2. Then it's a 0 that you can avoid calculating. This is the moment in which you have partial filling of the molecular orbital. So in the bonding orbitals, you have 2, 4, 6 electrons. In the anti-bonding, you have 4. So this will mean 6 minus 4 divided by 2, integer bond order. This is a single bond, and the molecule is stable. You can see here the shape of how the actual molecular orbital are going to look like for F2. So where do you put your electrons when they're bonding is not equally shared between, no, they have a new place where they can reside with a certain probability. If we move across from fluorine, the next option would be oxygen, same approach, 6 electrons in the valence shell. Here, this thing actually starts from the 1s, so it shows you all the closed shell. 1s and 2s, they will interact. You have 2 atomic orbitals, 2 molecular orbitals, 2 atomic orbitals, 2 molecular orbitals, full of electrons because you just filled everything up. This means that this shell will cancel each other out for the purpose of doing a bond order. Then this is a different representation that we had before. Before, the orbitals at the generate level were shown with 2 very close lines on top of each other. These are next to each other, but the meaning is still the same. This means that you will get a sigma and a sigma star with the direct interaction of the px, if you label everything properly. Then you will get the pi. The 2 pi are at the same energy because they're equally away from the direct bond. So you have 2 pi and 2 pi star. But this time, you have a different amount of electrons to fill. Instead of doing 2s2 2p5, this time you have 2p4. So now you're slightly out of electrons. And the hand rule in this specific case demands that you first fill both of the pi star and only after you start to pair. So you don't put 2 electrons here and leave the other one empty. They are at the same energy. They must be filled in parallel. The bond order here, same business. And you get a 2, which is a double bond, which we know from oxygen. The molecule is stable and it is a double bond. Note that this fact that you have degenerate p levels with a partial occupation is something that you account for with molecular orbitals and means that the molecule inherently in its molecular state has unpaired electrons. Oxygen as a molecule is inherently paramagnetic. This means it will react in some way to a magnetic field, whereas fluorine is diamagnetic, all the electrons are paired. If you want to check out what happens to liquid oxygen with this paramagnetic feature when you put it in a magnetic field, please check out the YouTube video that I'm attaching to this lecture. Same stuff, 1 electron less, we go to nitrogen. Once again, ignore the 1s shell, but predictably, the 2s shell is also filled. So this time, what happens when we consider the P? We have the same sequence, technically speaking, but now we are flipping over the sigma and the pi. If you do the filling, this time, given the flip that you find in the orbital, you don't have the problem of the unpaired electron. The calculation will say that everything here stays in the bonding orbital. There is nothing in the anti-bonding, which means you will find 6 divided by 2 equal 3. Nitrogen 2 is a stable molecule with a triple bond, which we knew. But now we see also something else. So this feature of flipping over the order, so you don't start with a sigma, but you start with a pi, is a feature of the difference in energy. This is called the sp mixing. So the sp mixing will arise as you move across the periodic table. So if you do fluorine and oxygen, as we did before, you start with a sigma, do the pi, pi star, sigma star. As you move across, the energies of the orbitals that you have become closer and closer and closer, which means at some point, making them interact will make them flip. The energy gain that you will get from the pi interaction is more, slightly more, in some cases, really much more than the interaction of the sigma. This means that pi drops in energy, the sigma is next. So then instead of having sigma, pi, pi star, sigma star, you have pi, sigma, sigma star, pi star. This happens as you go across the periodic table. The moment you flip from oxygen to nitrogen, you can have some sp mixing. So this, the similarity in energy of the S and the P, and the feature of the mixing of the S and the P is exactly the reason why you manage to use hybridization for carbon and nitrogen without failing miserably, because they are close. They are really so close that they are interacting with each other. The moment they interact with each other, in reality, the hybridization is sort of like a small toy theory of what it becomes the bigger molecular orbital theory. So now, instead of having an hybrid, we actually know where the electrons are in terms of region of electron density using the molecular orbitals. This is just with homonuclear. Nothing stops you from doing an interaction with two different atoms that are not the same, because you can have diatomic molecules with heteroatomic arrangement. The effective combination will still require similarity in energy. So you need to be very careful where are you looking at in the periodic table, because the electronegativity will tell you how deep in energy and how high in energy things will be, and if they can be combined with each other. More or less. Obviously, we don't want to have quantitation. Quantitative can be done, not at this stage. So if we do something for the NO molecule, then you have this dissimilarity between the two of them. So you have nitrogen that is bringing a certain, they bring the same amount of orbitals, but the amount of electron is changing. Oxygen is more electronegative than nitrogen. If it is more electronegative in the diagram, it will be lower. So we do approximate a bit, but we know they are close enough to each other that the energy should be comparable. By approximation, we put the 2s and the 2p of the atomic orbitals of oxygen slightly down. The one of the nitrogen will be slightly up by comparison. So you kind of need to then do the splitting around a central point, but the gain and the loss is not symmetrical to the two of them equivalently, because it's impossible. Right? So the moment you do this, then you also see the disparity of how many electrons these things are bringing. So you still get sigma, pi, pi, sigma star. This is a bit of a thing to consider, like the moment you start to do the crossover, in this moment you put oxygen on top of nitrogen, that is the vague beginning of the sp mixing. So we could consider that potentially we're not going to get the sp mixing, we do the sequence as it is. Note that given the arrangement is not going to be that much different. The bond order here, given this disparity, is going to be 2.5. So 2.5 means that you have something between a double and a triple bond. We know that this molecule is fluctuating. You might have done the resonance structures even in high school, and this is the reason you have a resonance structure, because you have this single lone electron. The fact that you have a single lone electron also means that this molecule in a magnetic field will behave like oxygen. It will react to the magnetic field because you have something that you could potentially align. There are then other more complex examples that we're not going to require as a thing that we do manually, because homonuclear, heteronuclear, diatomic can be done from first principles. In the moment you start to insert more molecules, so for instance, C and 2 oxygen, so you want to do CO2, you need 2 pairs of sets of the atomic orbitals, but then you can see here that the arrangement of how deep and how high something goes in the interaction is more complex and cannot be immediately defined from first principle. This is with carbon and 2 oxygens. This is with boron and fluoride. So how do you get that flat shape, and what is the shape of the actual orbitals that are bonding? They're over here. So the sky is the limit for the molecular orbital theory. You have nothing that you cannot do. You can account for every type of orbital at any type of molecular arrangement. This will be realistic. So it will actually be the way the molecule bonds. Doesn't matter for the level of complexity. Everything that is beyond a certain level of complexity, however, requires a computer. So a computer will calculate for you on your behalf everything that needs to be done in terms of energy. The bonding style that you have already encountered, so single bond, double bond, triple bond, partially ionic, how strong is this bond, is this a polarized bond, all of this will be accounted for how you distribute the electron density and how deep do you go with the orbitals. If you actually want to be able to do rendering and calculations, we do have a more advanced course, which is quantum chemistry, that goes together with molecular modeling, in which you do exactly this type of calculation. So if we go back to how we began, which is with these weird clusters of inorganic molecules that will not be accounted for in all the approaches that we did with organic chemistry. For instance, you could have a metal surrounded by ammonia around it. This complex in itself will have a molecular orbital description. How is the ammonia bonding? Instinctively, you could say, well, with the only thing that is not bonded, the lone pair, okay? If you do with the hybridized description, so you use the hybrids, you use the sp3 hybrids, you do the three-dimensional shape of ammonia, the lone pair goes up because it wants to be further away as possible as everything else. All of the sp3 are equivalent in nature, and that lone pair is over there by itself. When you actually do the molecular orbital diagram, you can see the complexity of trying to do the splitting, and you can see here that since we're using nitrogen and hydrogen, you have the sp mixing. The molecular orbital theory will reconstruct exactly the same thing, but your lone pair is not by itself. It is now in a molecular orbital. And the molecular orbital where you put the lone pair is not the same molecular orbital where the bonding electrons are. They are not in the same type of molecular orbital, whereas in the hybridization description, this lone pair is exactly in the same sp3 orbital as the other pairs that are doing the bonding. So this one is different. It has a significant p character from where it's coming from, because it's coming very close from p, and it belongs fundamentally mostly to the nitrogen. So it is bonding with whatever metal you put to do this complex, but the strength and this thing is coming directly almost from the nitrogen. It's almost unmodified from what it was in the nitrogen. So the molecular orbital with the lone pair will be the one that is interacting. It is not a lone pair on an sp3. So this is how we start to arrange this type of big complexes. What is the metal doing in this thing to be able to actually build the whole molecular orbital description? Well, this is going to be the topic of lecture 2. So about this, we're going to talk in the next week. We will move then into a systematization of all these weird arrangements that we've seen, so we make sure that we can actually address all the molecules that we're going to find.